complaint with respect to the choice of the questions and all those things. But in
Mm-hmm.
order to score it in the exam, that kind of a feel and that kind of a practice is required. So generally, if you can put extra question in the practice assignment, that will be helpful.
Yeah, yeah, absolutely. I think I'm in fact working on not just the practice assignments, but also I think I promised additional review assignments precisely to help with additional preparation for the exams, as well as just I think in general I think it's probably good to have more recap and review whenever we have a chance. So those will also be released, I would certainly hope by Friday, and will be available to you, and you can submit them by the last deadline I think is 30th August. So yeah, so the idea is to get some revision in. That's kind of the plan. Yeah, so I think I hope that addresses your feedback. And Arya, you have raised your hand.
So for the review assignments,
Yeah.
I just wanted to understand if they are being included in the like marking, as in like the final evaluation. Like I think in the mail you said that it will be included for the eligibility, but will it also be included for the grading per se?
I think so. I have to confirm with the team, but my suggestion was that you can basically, anyway, the grading I think is the top X assignments out of the total Y assignments that have been issued. So my suggestion was to include this in the pool of assignments from which the top X will be taken.
Okay, no, so in the grading, this thing, the document, it is said that top 10 out of 12, sorry, yeah, I think top 10 out of 12 will be taken.
10 out
So,
of 12.
but
Yeah.
what has happened is on the dashboard, it is showing the review assignments as week 8 assignment and week 9 assignment. So,
That is a bit odd. That was not quite the intention. I'll check what's going on with the team, but basically, I think one of the review assignments came in week 5, which was I think a planned break, and here I think yeah. Let me just check about what's the current status. So the review assignments that I referred to in the forums or that I'm talking about now have not been released yet. So those are basically review assignments that go over all the topics across all the, like we have basically done 10 weeks of material. Just to quickly recap, it would be greedy, matroids, dynamic programming, flows, NP completeness, approximation, randomization, exact, parameterized, and kernelization. So those are the 10 topics. So there'll be two review assignments basically covering 5 topics each. That's kind of the idea. And I'm hoping that that will go into the pool of assignments on which from which the top 10 will be taken.
okay, okay, ma'am, yeah, okay.
Right. Okay. So all right. So with that said, I think if there are no explicit questions, then let me just get started here. So um, I want to talk about the assignment that you have associated with the exact algorithms material. And with exact algorithms, the idea is that we want to make sure that we always produce a correct output. This is unlike, say, approximation or randomization, where we are willing to, sometimes in randomization, you allow for an error as long as you can bound the error probability. In approximation, again, you allow for an error as long as you can bound the margin of error. You can say that you'll never be off by more than a certain amount. But in exact algorithms, as the name suggests, you want your answers to be exactly right. So we are not going to compromise on the correctness of the output. So we want correct output on all instances. So, as you can imagine, you must compromise somewhere, as we have discussed when we talked about NP completeness. So, if you're working with a hard problem, the compromise is going to come in the running time. So, we may suffer, basically, we are beyond the regime of polynomial time algorithms. So your running times may look like 2 to the n factorial, n to the n, or worse. Okay, so those are the typical running times that you would encounter once you are in the regime of exact algorithms. And here again, just as you do with standard algorithms, your intention is to always ask can we do better? And so usually for a subset problem, you can get 2 to the n simply by doing brute force. You can enumerate all subsets and you have 2 to the n. And then whatever property you're looking for is usually, something that you can check in polynomial time. So no big deal. So then the question becomes, okay, we can do 2 to the n, but can we do like 1.9 to the n? Can we do 1.5 to the n? Can we do 1.001 to the n? Or maybe can we be even more ambitious and say, can we do 2 to the root n, for instance, or something like that? So those would be sub-exponential algorithms. Sometimes, for example, like traveling salesman, right? You want to know what is a route that passes through all the cities and that has the cheapest cost. And there, the brute force algorithm will be like n factorial. You can try all possible permutations, compute their costs, keep track of a running minimum. And I think if I remember correctly, this is one of the practice assignment problems to improve this using dynamic programming over subsets. And the spirit of the DP is kind of similar to what you see when you do, for instance, we have done the set cover DP in the past, the DP over subsets. So it's kind of in a similar spirit. So that's an improvement from n factorial to 2 to the n. In the videos, you will see an example involving chromatic number where you're trying to color a graph properly. So there, the brute force algorithm will roughly, take the form n to the n, and then we try to improve that to something like 3 to the n, 2 to the n, and so on. So those are the games we play. Basically, we try to do as good as we can on the runtime, um, uh, given the fact that, okay, we're definitely not going to end up with polynomial running times unless you make additional assumptions on the structure of the input. Like, for example, we have seen this before. Like, if you are working with independent set, for instance, in general, it's going to be hard. But if you have like a dance class kind of situation where you're trying to find an independent set, you're focusing only on graphs that have this very nice interval kind of structure, and then you can manage in polynomial time. Similarly, we saw with this clique and box depth, so you can solve a clique like problem more easily if you have some kind of a geometric crutch that you can sort of work with. So sometimes making additional assumptions on the input makes your life easier, and then maybe you can go all the way to devising efficient polynomial algorithms. But that's not the focus of what we are doing here. Our focus will be to solve a hard problem in its full generality, solve it properly, always produce the correct answer, but somehow do it in style. So instead of getting some horrible brute force running time, we want to see, can we do something clever and bring down the running time as much as possible. So that's the premise of this week. If you haven't watched the videos yet, then basically I have the speech in the beginning and then we go over a couple of examples. And I basically wanted to focus on a particular technique which uses, it's called the technique of inclusion exclusion. And I think I already demonstrate this in the videos for the chromatic number problem, but I'm going to give you one more example here, which will lead up to the assignment problem. So let me go over, let me just write down the inclusion exclusion formula. Okay, so this is something you might remember from, I don't know, maybe even school or other courses. So let's say that we have n subsets, A1 through AN, of some universe U, and we want to know what is the size of the intersection of all the AIs. So normally you might have seen this formula for union. Normally we count the size of the union, but you can apply De Morgan's laws on that formula to get to this one that I'm writing down. And the reason I'm writing it for intersection is because this is the version of the formula that we will find useful. So the way this formula works is that we for all subsets of 1 to n, which is the index of the collection of sets that we have. So we have A1, A2 up to AN. So I'm going to go over all subsets from 1 to n. And I'm basically going to look at the size of the intersections of AI complement. So AI complement is U minus AI. Okay, and here I'm really interested in taking this intersection only over elements of X. So excuse me. And the reason this is inclusion exclusion is because we have this multiplier, which is minus 1 raised to the size of X. So for instance, if we just had two sets, A1 and A2, then all that this boils down to is, okay, I just wanted to confirm that I haven't lost my connection. Okay, yes. All right, so A1, A2, what does this boil down to? This basically says A1 intersection A2 is going to be, let's go over all possible subsets. So for instance, for the singleton set 1, we're looking at the size of A1 complement. The singleton set 2, we're looking at the size of A2 complement. Um, and for these singleton sets, this will actually be a minus, because minus 1 to the size of X is minus 1. And then when we look at both of them together, we are looking at A1 complement intersection A2 complement. And there's one more term that corresponds to the empty set. So the empty set by convention is going to be the size of the universe. Okay, so I'm going to add that in as well. So those are the terms that I get. Let me see if it's useful to put this on a separate slide and maybe relate it with a picture. So this is when X equals empty set. This is when X equals the singleton set 1. This is when X equals the singleton set 2. And this is when X equals 1, 2. Yeah. And this is the size of the intersection. And basically, what are we saying here? We said, well, we only wanted to count things in the intersection. So when my first term counts everything in the universe, then of course I've counted a lot of things that that I don't want to count. So I'm going to fix that by subtracting A1 complement. So when I subtract, let's say this is A1, this is A2. So when I subtract A1 complement, I'm getting rid of, everything here. So the elements here sort of survive. When I'm doing A2 complement, then I'm getting rid of, okay, maybe I should make a copy of this. Right. So every element in the universe at the end of the first term was getting counted once, right? And now what we did was in the second set of terms, A1 complement plus A2 complement, when we subtracted those, then we knocked out a bunch of those that are not interesting. So what we really want to do is we want to count these. So we want to preserve these elements, but we want to subtract everything else that has been counted and that is extra, right? So we are going to get rid of everything that's highlighted in blue and everything that's highlighted in red. So that's great because you got rid of these unwanted elements and these unwanted elements. but you got rid of everything that is outside, you got rid of them twice, right? So you have over subtracted or you've over corrected, and that's why the stuff that is outside both A1 union A2, that is A1 complement intersection A2 complement, that stuff you add back once to account for this overcorrection. Okay, so hopefully that makes sense. This is like one special case of the formula. The more familiar form of this formula may be the one where you say A union B is the size of A plus the size of B minus the intersection. Because when you're trying to take the union of two sets, you basically count their sizes individually, but then you realize you've overcounted the intersection. So you subtract it, and then you get the correct count for the union. If you have three sets, then you'll subtract the pairwise intersections, but then you will add back the three-way intersection because you've over subtracted, so you have to make an addition to correct for what you have overdone. So that's the more familiar form of inclusion exclusion. I think that's how it's normally introduced. But like I said, you can just apply De Morgan's to change your unions to intersections, and then this is what the formula looks like. This is the general form, and that's what we are going to be working with. Now, you might wonder, well, why does inclusion exclusion help with algorithms? And let me give you maybe a simple example first, which will kind of motivate. Again, like I said, in the videos, you will see this being worked out for chromatic number. But let me give you maybe arguably an even simpler example. So I don't know if you're familiar with the concept of a walk in a graph, but let me just say it out loud. So, okay, maybe I should start by defining the problem I'm interested in. So, I'm interested in the Hamiltonian path problem, where we are given a graph as input, and we want to know, is there an ordering of all the vertices? So, is there an ordering sigma, which is such that you can write this down. You can write down the vertices according to the sequence sigma, and this would be basically a path in the graph. So all consecutive pairs have an edge between them. So this is called a Hamiltonian path. It's a bit like traveling salesman, except you don't have to worry about edge weights and things like that. So I guess, for instance, here you could start here, go here, go here, okay, come in here, go around, and that would be an example of a Hamiltonian path. So for convenience, I'll just label these vertices in the order of their appearance on the path, so that sigma is just the identity permutation. Okay, and you could also ask for a Hamiltonian cycle. That's just you circle back to where you started. So if you want a Hamiltonian cycle, then you want to be able to come back to where you started. And the question is, does a graph have a Hamiltonian path or a Hamiltonian cycle? You can ask either of these questions. And notice that the brute force algorithm for both of these problems is going to be something like n factorial. You can try out all possible sequences of all the vertices. For every sequence, you can easily check if it's a valid sequence or not. You just go over the whole list, right, and check for every consecutive pair of vertices. Are they adjacent or not? That's straightforward. A good exercise is to try and improve this to a 2 to the n dp. What you can do is, just like we did in set cover, for every subset of vertices, you can ask yourself, well, does this subset induce a Hamiltonian path? Does this subset induce, for a cycle, maybe you have to do it a little bit differently, but yeah, basically, if you ask this question of every subset, you can, when you have addressed the question for the subset that's the entire vertex set, you will have your answer. And the base cases are also pretty easy to do because there's nothing to do for singleton subsets. So the question is, can you come up with the right recurrence? So again, I think there are some hints to how to do this for the related problem of DSP. So in the practice assignment, so I won't delve deeper into this here, but essentially you can do DP over subsets. You can get to 2 to the n. But one challenge with DP is that because this is an exponential time DP, it's also an exponential space DP because this is a exponential sized DP table to keep track of. And we want to see if we can improve this to something like polynomial space. So that's where this inclusion exclusion idea comes in. So the philosophy of inclusion exclusion is that we are going to try and describe um, the object that we are interested in as an intersection of some other objects which are computationally easier to handle. Okay. And therefore, you will get to your final answer by just carefully employing the formula. So let's talk about what are these easier objects. So one of the things that's a challenge um, uh, with paths is the fact that vertices are not allowed to repeat. So that's something you have to be sort of very careful about. So even in a DP solution, basically, if you have maintained a partial solution so far and you're trying to extend it, you have to be careful that you don't reuse any of the vertices that you've seen so far because paths are supposed to only involve distinct vertices. But there's this related concept of a walk. What is a walk? It's just basically it's a
Uh,
sequence of words. Yeah.
so,
Sorry, was there a question? Go for it.
yeah. So we cannot repeat the text, right? But so are cycles considered to be paths or not considered to be paths? I
Okay,
get
right.
confused quite sometimes, yeah. Because the last vertex is repeated, right? And
The
first and
last
last are the
vertex
same.
is
Yeah.
correct. So the last vertex is repeated. So I guess um, yes. So a cycle is well, it's not strictly speaking a path for the reason that you just mentioned, but at least what when people say cycle, they typically mean a simple cycle, which is to say that there's okay. Let me see. Let me give you an example of something that one normally would not call a cycle. So if you have something like this, right? So I don't think there's any way that you can write this down. So let's see. Yeah, so a cycle, a simple cycle is basically exactly what we just said. It's a list of distinct vertices. So I want to have, v1, v2, v3. So this is a cycle if the following edges are present, right? So V1 to V2 is present, V2 to V3 is present, V3 to V4 is present, V4 to V5 is present, and V5 back to V1 is present. So all of these edges are present. This is called a cycle. But this list of vertices itself should not have any repetitions. That's a useful way of thinking about it without getting confused. Does that make sense?
Yeah, so but in this case, like V1 would be repeated, right? Cycle as part of the
Well,
cycle.
so I
So
mean, yeah, so don't think of it as V1 being repeated because, in that sense, no matter where you start, you can say that this is a cycle from V2, V3, V4, V5, V1 back to V2. So then you can also say that in that sense, V2 is also repeated. So that's probably not, that could be a trippy way of thinking about cycles. So think of it as a list of distinct vertices such that every consecutive pair of vertices on that list has an edge between them, just like you do in a path. But then you also have an additional edge from the last element in the list back to the first one. That's all that it is, really.
okay, but strictly speaking, like a cycle is not a path, right?
Well, a cycle contains a path, right? So it depends on what you. So really, the set of edges is what you're talking about when you're making this distinction. When I'm talking about a set of vertices, right? So, for instance, um, you could have. I don't know. Let me just draw something out. So let's say we have a set of vertices here. So the question is, this set of vertices, strictly speaking, if you look at the whole thing, it contains a path, it contains a cycle. Um, so what do we exactly mean by this? So really what you're focusing on is, when I'm talking about a path, what is the path? The path would be this sequence of edges is what would constitute the path. And then you say that this set of vertices, along with this sequence of edges, that is what constitutes the entire object, which is the path. I don't know if that is useful, but let me just check with Prashant. Did you have a question?
No, not a question, but the same question I had in the artificial intelligence module. There,
Okay.
it was answered in this way that it is matter of convention, and both the conventions are used in literature to mention the cycles. Sometimes they do mention the first vertex again, and in some no, not. But in most of the time, they do not mention it.
Okay, right. I mean, so let's see. I mean, of course, you can have paths which are not cycles. So, for example, if this edge was not here, was not present in this graph, this would be a graph which has a Hamiltonian path, but it does not have a Hamiltonian cycle. I don't think there's any way that you can write this down. So there isn't a, basically, this would be a question of, yeah, I mean, to some extent, I suppose, okay, there are many things which are a matter of convention. So, for instance, when people talk about paths, some people have the convention that if you really want the vertices of the path to be distinct, then you should call it a simple path. Otherwise, for some people, something like this. Okay, sorry. So something like this. Um, would also be a path where, or something like this. This is a path for us as well. But let's say you go back here. Um, yeah, so let's say something like this. So I say P, Q, S, R. Um, where am I coming back? Yeah. So I go from P to Q, Q to S, S to R, R to T, T to S, and then S to V. Right. So in some sense, S is a repeated vertex here, and some people have this convention that that's also a perfectly valid path, and they would say that, well, if you want to emphasize that vertices are not repeated, then you should call it a simple path. Whereas in some other textbooks, this would be an example of what is called a walk, and and a path is basically you don't allow repetitions. Um, that is a matter of convention, but the distinction between, and okay, when you have a cycle, do you list the last vertex again or not, could also be a matter of convention. I think it's a matter of whether you want to think of it as a sequence of edges or a sequence of vertices. So some people will, okay, so you would sometimes write, so there is this notation where I think you talk about something like this VPW, where P is a sequence of vertices starting at V and ending at W. So if you specify the sequence and you call it P, so let's say you say P is defined as V, X, Y, P, W, something like that, then sometimes you will write this as a shorthand to denote that this is a path from V to W. And if you really mean the cycle, then you would write something like this, where what is intended is that you're looking at, all of the edges, including the last edge that kind of comes back. But what I'm saying is to think of this as a sequence of vertices with one repetition, that to me sounds a bit confusing, because then the issue is which is the repeating vertex. You can start anywhere you want on the cycle, right? So to me, that gets a little weird. So I think the simpler way of thinking about it is to think of it as a sequence of vertices and a collection of edges. Okay, if the collection of edges is such that it connects all the pairs, all the consecutive pairs in your sequence, then that is a path. But if you get all the consecutive pairs, but you also circle back to there's that one extra pair. So basically, if you have a collection of, some, okay, so if you have a collection of some k vertices, v1, v2, up to vk, then if you have a path, then you're looking at a collection of k minus 1 edges. And those are just all the consecutive ones, v1, v2, and so on. Or in general, I would say vi plus 1, I ranging between 1 and k minus 1. And if you're looking at k edges, so then I'm looking at vi plus 1, I ranging from 1 to k, where I plus 1 is taken mod k or something like that. So that when so maybe it's more convenient for this notation, it's more convenient to start with 0, I guess. So v0, v1 up to vk minus 1. And here maybe we start from 0 and go all the way up to k minus 2. Here we go up to k minus 1. Start with 0, but then when you are at k minus 1, then you have vk, but vk does not exist as a vertex in this collection. So I'm going to say we are going to go mod k, so that when I is equal to k plus 1, when I is equal to k minus 1, you're looking at vk minus 1 vk mod k. So k mod k is basically 0. Does that make sense? So then that gives you the last edge as well. So the path would be this list or this sequence of k vertices along with these k minus 1 edges, with the property that the k minus 1 edges are these specific edges. And for a cycle, it would be this sequence of vertices, again a sequence of k vertices, now with k edges, with the k edges specifically being these k edges. So does that help, Arya?
Okay for me, ma'am.
Yeah, okay for you. Thanks. Yeah, so I hope that this also addressed for Arya. Think of it as, yeah. So the important thing here is that this is a distinct collection of vertices. That would be a path in a cycle. But if we drop this condition that they're distinct, then not necessarily distinct, then you get what is called a walk and this one would be called a closed walk or a circuit sometimes, because you, again, the distinction really being that you come back to where you started. There is an intermediate concept of like a trail, which is something where you allow for the vertices to repeat, but you forbid the edges from repeating. But in a walk, basically, normally you wouldn't care. And of course, all of these things carry over to directed graphs as well, but I'll not kind of go into that specifically. So, anyways, I think yeah, sorry, Prashant.
From definition perspective,
Yeah.
it must be unique. And if we find uh, any kind of a such path, then starting from any other point, not the one that we have mentioned just now, but starting from any other point, then we must that also be a member of that definition. Then it becomes a closed loop or circuit. So
Right. So basically, again, I think just to clarify, so if you have, yeah, I mean, in some ways you can think of these as the same objects, but suppose I have this sequence A, B, and C, and I give you the edges A, B, B, C, and C, A. This would be a cycle. It would also be a closed walk. Because in a walk, you don't demand that vertices repeat. They can repeat, but they don't have to. I suppose something like uh, this would also. So let's maybe look at an example of a walk, which is not a cycle. So you can go from A, B, C, D, E, C, and then F. And then I'm saying A, but that is implicit because, like we just said, what this is this collection of vertices. In fact, not just a collection, it's a sequence of vertices. So this is a particular sequence. Let me call it S maybe. And the edges, as you can see, all the consecutive edges are present. So AB is present, that's this one. Then we have BC, that would be this one, and so on. We have CD, DE, EC, CF, and because I want to claim, I want to define a walk here, I'll also come back to FA. If I had only stopped here, then this would have just been a walk. But if I include the last edge in my object, then that's a closed walk. And so this object, this particular sequence of vertices and this collection of edges is one closed walk. I could change the sequence and I could sort of say, okay, let's start at BC, let's start at B instead. And we sort of keep going. So it's the same thing, and you will again come back all the way to B. Um, that's also a valid closed walk, and there is a sense in which they're effectively the same. So you could say that I treat two walks as the same if they are kind of essentially the same sequence with different starting points. So if you view them as sets of edges, then you basically have the same set. You're just traversing them in a different order. So often you will say things like, well, if I say I want to count the number of walks, am I counting it, up to symmetry, or am I counting, yeah, so basically, do I want to treat these objects as same or different? That could be in some sense a matter of convention, but otherwise, hopefully in terms of the definition, it's clear that really a walk or a path or a closed walk or a cycle is a sequence of vertices bundled with a collection of edges, which in some sense is compatible with that sequence. So it gives you all the consecutive pairs plus that extra one, depending on whether you have a path or a cycle or a walk or a closed walk. So this is okay.
yes, ma'am.
Awesome. Thanks. Yeah, so just to make sure that I think I addressed your question, I think your question was about, like, the choice of starting point. And the way I'm writing it here, each choice of starting point gives you basically a different object. But you could always say that in my application, I want to treat these objects as the same. So, I'll say that two walks are equivalent. And then you
Mm,
could sort of, not count them as being distinct.
yes, yes.
Right. Okay. So it turns out that walks are much easier to deal with algorithmically compared to paths. And the reason for that is that if you take a graph and you write down its adjacency matrix, which you may have seen in data structures. So, for instance, the way the adjacency matrix works is that okay, so this entry is a 1 if, say, 3 comma 4 is an edge and is 0 otherwise. So in general, the idea is that the ijth entry in this matrix is the ijth entry in the adjacency matrix of a graph G is 1 if, so assume that the vertices are labeled from 1 to n. And so I'm really thinking about ij going between 1 and n. So if I and j have an edge between them, then I'm going to put a 1. I'm going to say 0 otherwise. Okay, so that's the definition of the adjacency matrix. And now the question I want to ask is, what can we say about the ijth entry in A squared? So suppose I were to square this matrix, A squared, what would be the ijth entry? So the way we know matrix multiplication works is that you're going to get the ith row of A and you're going to multiply it by the jth column of A, and that's how you get the ijth entry in A squared, right? Now the entries in the ith row that are 1 are basically the neighbors of the vertex I, because if the ikth entry is 1, that means that ik had an edge. So from I, all the neighbors that I have, those are going to be the 1 entries. And similarly, it's a symmetric matrix for an undirected graph. So all the entries in the jth column that are a 1 are basically going to be the neighbors of j. So if there is some vertex which is common to both I and to the neighborhood of I and j, which is like, let's say, some vertex k, then that will contribute to the count of this sum. Otherwise, basically, it's going to get knocked out, right? So basically, this guy here is counting the number of, in some sense, common neighbors of I and j. Is that clear? Okay, great. So the other way to think about this is that it's kind of counting the number of ways in which you can reach from I to j using two edges. So, all the different ways of that you can do this. If you're just looking at the adjacency matrix, it's basically telling you, is there a one hop path or not, right? I'm saying path, but technically what's going to happen is that we are going to actually be counting walks. So in A, you're going to have, you're just going to be counting direct edges. Okay, welcome back, Arya. No worries. I think what you could do is maybe just check the recording and then let me know if your question from earlier was addressed. We did try to go over it, but I'm just going to. Okay, thanks. Yeah, I'll just continue from here. What we just defined is the adjacency matrix, which I figure you have seen before. The ijth entry is a 1 if there is an edge between I and j. And now I'm just saying that the ijth entry in the square of the adjacency matrix basically gives you the number of ways of getting from I to j in one hop. So it's counting the number of common neighbors. So in the adjacency matrix raised to the first power, which is to say we are not doing anything. We are just counting if there is a one hop connection between I and j. Here we are asking for a two hop connection. Now, if you think about what's going on with A cubed, right? So what's going to happen with A cubed is that you're going to multiply the ith row in A squared with the jth column in A, right? So here, what is going to survive is, well, I mean, here I have an entry, a one entry from I to k, or in fact, okay, in A squared, from I to k, I've counted the number of one hop ways of getting to k. And now if k happens to also be a neighbor of j, right, then, well, I'm going to, this entry is going to survive. So I'm basically going to count all the ways of getting from I to j now in three hops, that is to say using three edges, because there will be some k1. So when I'm looking at the ith row in A squared, let's say the one entries are at some k1, k2, k3. So let's say ik1 is, well, not a 1, but as an example, let's say this is 5, 3, and 2. So for K2, there are three 2-hop connections from I to K2. For K1, there are 5 of these. And let's say there is an edge from K1 to J as well. But let's say for K3, there is no edge from K3 to J. So when you multiply the ith row with the jth column, the K3th entry in the jth column is a 0. So let's say this 2 gets knocked out. So what you'll be left with is 5 plus 3 equals 8. But what is this 8? It's basically counting all the ways in which you can get from I to J in 3 hops, right? And you can imagine that if you generalize this and you ask for the ijth entry in the matrix A raised to the lth power, right? So when we raised it to the third power, we got all the 3-hop connections. When you raise it to the lth power, you get all the, like, the number of L length walks from I to J. And the reason I'm saying that it's walks is because we really have no control over whether vertices are repeating or not when you are making these connections. So when you're seeing something from so when in the A raised to L minus 1 wala matrix, when I'm looking at the IK1th entry, or let's say just some ikth entry, and akj is also 1. So this guy, if this guy was 7, then then 7 is going to contribute to the count of this fellow here. So 7 is going to contribute to that count because 7 will get multiplied by 1 when you take the ith row and the jth column. But what is the 7? It's counting the number of ways you can get from I to K in L minus 1 steps in using L minus 1 edges. But for all you know, from I to K in making that journey, you may have used the vertex J somewhere. That's quite possible. And then you're coming back. Then when you're reaching J, you're again, so basically you're seeing a repeated vertex. And that may easily happen. So this quantity here is not necessarily counting paths. And yeah, okay, so you're talking, okay, it reminds you of Floyd Warshall. Perhaps, yes, because of the sort of the recursive nature of the whole thing. That's probably, I think Floyd Warshall is this DP based thing for finding shortest paths. So yeah, it's not surprising that you're reminded of that. The only thing is here, the matrix multiplication is completely oblivious to repetitions. So it's not going to disallow repetitions necessarily. So what we have here is basically all possible walks that take you from I to J in L hops, or using L edges, right? So hopefully that claim is clear. If not, just take some time and maybe look at some small examples. You can formalize it using induction. The induction hypothesis will apply to all lower powers. The base cases we've more or less worked out with A and A squared. So it's not a difficult thing to actually prove formally if you would like to. Okay. So the main thesis of all of this is to say that counting walks is easy. Okay. You can count walks without too much difficulty. But now what we are interested in is paths. So we are going to do this very, very neat trick where we are going to define AV as all walks in G of length n that contain the vertex V. Okay, so we are going to say, so in fact, if we want to do, let's say we want to do Hamiltonian cycles, because if you want to refer to this from a book, you can go to the parameterized algorithms book. I'll drop a link to that reference. So I think if I remember correctly, they basically do Hamiltonian cycle, but you can do the same thing for Hamiltonian path. It's really very similar. So let's say that AV is A sub V. So for some vertex in the graph G, it's the collection of all closed walks in G of length n. So basically, I want to say that you by length n, I simply mean that every vertex was visited in this closed. Well, okay, the number of vertices that was visited. I don't want to say every vertex was visited. I want to say that the number of vertices that was visited in this walk is n. Okay. So this is a set. So this collects all closed walks in G of length n that contain V. Okay, so I'm taking some sequence of vertices. So let's say V sigma 1. Or I don't know if that's going to be confusing. So let's just say um, this is some sequence of vertices. Potentially vertices are repeating, I don't care, but it's a closed walk in the sense that all consecutive edges are present. The last edge back from un to u1 is also present. And the point is that one of the UIs, at least one of the UIs, is equal to V. So we are looking at all closed walks that contain the vertex V. So hopefully this definition is clear. And what I claim that what we are interested in is the intersection of AVs over all vertices V in the graph. What can we say about this intersection? Notice that what kind of closed walks would belong to the intersection. First of all, it has to be a closed walk of length n. Otherwise, you don't even belong to any of the individual sets, so forget about belonging to the intersection. But the point is that if you have to belong to the intersection of these n sets, then you must also contain all the vertices because you belong to AV for all V to belong to the intersection. So this is really the key idea. Does this make sense? Okay. So the size of this intersection is really counting the number of Hamiltonian cycles in G. And so these are basically the walks which are not paths because, sorry, the other way. These are the paths which are not walks in the sense that they don't have repeated vertices. Because the point is that you only have, n slots and you must visit or you must contain all the n vertices. So there is no space to repeat anything. It's not possible to have a repetition because let's say this is a graph on 4 vertices A, B, C, D. Then I know that I have 4 slots and I have to fit in all of A, B, C, D in one of these slots, in separate slots, of course. So if I must do that, then I really don't have the space to repeat. So the only thing that would make it to the intersection would be things that are really walks, closed walks that do not repeat vertices. Okay. All right. So Arya, I think you have a raised hand.
Ma'am, so my question is that we took an example earlier, right, wherein you said that we can say that the cycle starts at 1 or cycle starts at 2 or cycle starts at 3 or
Correct.
something like. So this AV set that would contain all such paths slash cycles slash everything, right?
Right. So if I define the walk as a sequence, right? So then it's going to catch all of these sequences. So something that is effectively the same sequence will show up. Well, I mean, let me just be careful about confirming this. Yeah, I think once we take this up as I think I defined this earlier here as something that is a sequence and a collection of of edges that's associated with the sequence. So that is going to get I think that is going to get counted separately every time. So let me just uh, when you're doing the matrix multiplication, for instance, if you're going to be looking at closed walks that go from um, yeah, basically closed walks that go from 1 to 1 versus 2 to 2. You might be looking at the same walk, but basically at just like rotated 1 unit. So all of these will indeed show up separately.
Yeah, okay, ma'am. Yeah.
Right. So if you want to treat them as being separate, basically, then you can always factor it out from your final count. But for now, all we want to know is if there is at least one Hamiltonian cycle or not. So all that we will kind of care about is knowing if this quantity is strictly greater than zero or not. That's all that we care about.
Ma'am, but uh, I'm not then fully convinced of this cycle part. So when you say it's a Hamiltonian cycle, so essentially the example that you took was that then that means that there would not be any repetition of vertices, right?
Right.
Essentially,
So
they would be reduced. All the walks would be reduced to cycles, right?
correct. So once again, think of this as a sequence of n vertices. So this is a cycle. It's this vertex sequence along with this list of edges. This object is what I'm calling a cycle.
Okay, so even in the case that we were previously considering, which is when the
Right.
same kind of cycle, but albeit with a different starting and ending point,
Right. So
so
this would
it
be
would still
sequence.
reduce down to the same sequence in
Well,
some sense.
I mean, so this would be another sequence if you like.
Okay, but when I take the intersection, so both of these are not common, so neither of them will be taken. Are you saying something like that?
Not necessarily. So this sequence or this object will belong to A sub A, will belong to A sub B, will belong to A sub C, and will belong to A sub D. Right? Because what is A sub A counting? It's counting all the closed walks which contain the vertex A and that have n vertices. So let's say n is equal to 4, right? So this sequence here will make it to all the sets because it contains all the 4 vertices and it has length n.
Okay, okay. So the intersection that we're taking is
Yeah.
not on the sequences, but rather the vertices themselves, right? And the sequences that are
Okay.
associated with the vertices.
Okay. Now, so let me just clarify. So AV, so maybe it's useful to do this with an example. Um, mm, right. So let me write down a sequence maybe here. So W, X, Y, Z, Y. This would be a sequence of, um, so let me see if this is a closed walk. It is W. You can go from W to X. Sorry, can't go from W to X in this current. So we have W to X, X to Y, Y to Z, and from Z back to Y. Um, that's and from Y to W, right? So that's if you just follow the edges, I go from W to X, X to Y, Y to Z. I come back from Z to Y, and then I take this edge from Y to W. So this WX, XY, YZ, ZY, YW. So this object is what I'm calling a closed walk, right? This is a walk that, remember that as far as a closed walk is concerned, there's no problem with repeating vertices. Okay, so vertex repetitions are allowed, and this is one closed walk, but you could also have another one which moves a bit differently. So let me make a copy. So this is a closed walk of length 5 in the sense that it has 5 vertices. Let me do a, oops. Okay, so let's go from V to W, W to X, X to Y, Y to Z, Z back to V. So I'll start this wherever I want. W, X, Y, Z, V. And here the edges I'm looking at would be WX, XY, YZ, ZV, and VW. Okay, so these are both closed walks. This I'm interested in, this I'm not interested in. Okay, this is the second one is a closed walk that's also a Hamiltonian cycle, but the first one is a closed walk that's not a Hamiltonian cycle. Does that make sense?
Yeah, yes, ma'am. Yeah.
Right? Okay, so now when I'm looking at the set A sub V, A sub V will contain this guy because this is a closed walk that is of length 5 and that has the vertex V. But A sub V will not contain this fellow because this does not contain the vertex V.
Yeah, okay.
Right? Okay. So the point is that any closed walk that is not a Hamiltonian cycle will necessarily, because it's repeating at least one vertex, it is necessarily missing out on one vertex at least.
Yeah, I think, yeah, okay, that makes sense.
Correct. So
Hmm.
whatever you're missing out on, you will be knocked out of the intersection because you will not belong to that particular set.
Okay.
Right?
No, just kind of trying to demystify this expression on the left-hand side.
Right.
So when you have this intersection AV and V belongs to vertex set of G, right?
Correct.
So basically so AV is the set of all closed walks of length n that contain V's, and V can be any vertex from the vertex set, right? So we
It
will
can be
have.
any vertex, but it's the specific vertex. I mean, this way and that way are the same.
Yeah. So basically, so if there are like five vertices, so A1, A2, A3, A4, A5, something
Correct.
like that, and
Yeah.
all
So in
kinds
this
of walks,
example, you will have these 5 sets.
right?
Correct.
Yeah, and now using the property that you recently stated, which was that every time I make so if there is not a Hamiltonian cycle, so I miss out on one of the vertices.
Correct.
So
Exactly.
essentially, that means that this intersection that I'm taking the intersection over the entire vertex set. So
Correct.
that means this is VWXYZ, and then eventually whatever I get, that would it has to include all the vertices, and in effect, that would basically mean a cycle because a non-cycle cannot achieve that. That is what you're trying to say,
Yeah.
right?
Yeah. Exactly. So by the time I'm a closed walk that belongs to all of these guys, right? So first of all, for me to have membership into any of these sets, I must be a sequence of 5 vertices because all of these sets only contain sequences of 5 vertices along with the appropriate collection of edges. So if I want to belong to any of these sets, I have to be a sequence of 5 vertices. But if I'm in the intersection of all of these sets, then in particular, because I belong to AV, one of these 5 vertices must have been V somewhere. Because I belong to AW, one of these vertices must have been W. Because I belong to X, one of these vertices somewhere must have been X, and so on. So basically, I have to, if I want to belong to the intersection, I must catch everything. But because I have only n slots and n things to catch, there is now no room left for repetition. So I must have I must have seen every vertex exactly once in this sequence if I belong to the intersection,
Okay.
right?
And one maybe a rather trivial doubt, but point is, how do we know it's not a Hamiltonian path, but always a cycle?
Well, because the objects that we are counting here are cycles. So if you look at the edges that are bundled with these sequences, right? I'm deliberately defining them to be closed walks. So the moment I say that this sequence of vertices is being counted as a closed walk, then by definition you get that extra edge. Of course, if you have a Hamiltonian cycle, then you also have a Hamiltonian path, but not the other way around.
Okay, okay, got it.
Yeah. So that's just basically by definition. Okay. So because I'm talking about closed walks. Okay, so now hopefully it's clear that this object here, which is the intersection of all the AVs, is the count that I'm interested in. If this count is strictly bigger than zero, that means there must be at least one Hamiltonian cycle. But if this count is equal to zero, then that means there is no Hamiltonian cycle. So the way we are going to do this is by saying that, okay, what is the intersection of the AVs? By the inclusion exclusion formula, I know that I want to go over all the subsets of the vertices. I have this multiplier. And what is the term here? I'm looking at the size of the intersection of AV complement for V and X. So let's just try and understand what is AV complement. AV complement is, well, our universe is all closed walks of length n. Okay. So when I take the complement, I'm interested in all the closed walks that avoid V instead of containing V, right? So AV partitions the universe, like basically AV is picking up all the walks that visit V. AV complement will be the rest of the walks which by definition don't have V. Does that make sense?
Yes, ma'am.
Okay, great. So now if I take AV intersection, say AW, what does that mean? That means, AV complement intersection AW complement. What does that mean? That means, well, AV complement is all closed walks of length and that avoid V. AW complement is all closed walks of length and that avoid W. And intersection is AND. So now I'm saying I want all the closed walks that avoid both V and W, right? Okay, so if I come back here, okay, I have to wait for the screen to update. Yeah, so if I come back here, what is this count? This count is the number of closed walks of length n that avoid all of x because I don't want to see anything from x. Okay, does that make sense? I think hopefully this is clear.
Yes, ma'am.
Yeah, because I want to avoid if x is like V, W, P, Q. Then AV complement is closed walks that don't touch V. AW complement is closed walks that don't touch W, that don't touch P, don't touch Q. And now we're doing an AND over all of this. So we don't want to touch any of this. So if I know how to count this object, then basically I can take all subsets of the vertex set, perform this count, and keep track of a running sum. I just have to add or subtract depending on whether if the size of the set I'm looking at is even, then I'll add it. If I'm looking at an odd sized set, I'll take that count and I'll subtract it. But what is this count really? So I have my graph G, and if I'm trying to figure out all closed walks that don't touch anything in X, what I can do is I can take X and delete it from the graph because I never want to look at any vertex in X. And in whatever is remaining, which is G minus X, I can look at the adjacency matrix of G minus X and raise it to the nth power. The ijth entry here will give me the number of basically open walks that go from I to j that have n vertices, And so I'll only look at those ij's that have a direct edge between them, so that this loop is closed basically. So essentially, by taking matrix powers, by raising the matrix to the nth power, you can essentially look at, in fact, you can probably do something even easier. You can look at just look at the diagonal entries here, because that will give you basically automatically closed walks that come back from, so the diagonal entry for one will be all the closed walks of length n that go from that begin at 1 and end at 1. That's just when we made this claim earlier about the nature of the kth power of the matrix, if you apply it to the diagonal entries, you will see that you're basically counting the closed walks. So you can so if you're trying to avoid a particular subset, then you can get rid of that subset and then do this nth power computation, and these diagonal entries will give you will basically give you the correct count. So the high level idea is that these intersections here that show up in the terms of the inclusion exclusion formula, those intersections are easy for us to count, in the sense that they're actually polynomial time, because you can raise a matrix to the nth power in polynomial time. In fact, there's a nice way of doing it using divide and conquer as well, where you only compute the n by 2th power of the matrix, and you basically multiply that by itself to get the nth power directly. So you can even do this quite efficiently. So by computing a diagonal entry in the nth power of g minus x, you can calculate the value of this term here. And now you can just alternately add and subtract these terms based on whether or not the size of the subset that you're working with is odd or even. And the main advantage of doing this over DP is that you don't need exponential space. All you need is a running counter which keeps track of the sum, and all your computations are basically throwaway. You just work with a different adjacency matrix every time. You don't have to remember anything. You just update a running sum, a cumulative sum as you're going along. And then at the end, you check if everything cancels out and it becomes zero. If the sum becomes zero, then you say there is no Hamiltonian cycle. But if you get a non-zero entry, then at that point you do have uh, evidence that there is at least one Hamiltonian cycle in the graph, and then you can report yes. So does the maybe some of the details, I don't know if they were rushed, but does it make sense that this works? Okay, cool. So if the starting point of the walk is still confusing, so the way I said it, you are going to basically end up adding up all the diagonal entries to count all of the closed walks, and the count that you will get will have this basically additional multiplier of um, of n, because of the fact that your walks can start anywhere. So if that's something you don't like, because these walks are in some sense essentially the same, then you can either sort of divide by n at the end to get the count of truly distinct walks, or what you can do is you can also adjust your definition of the universe to say that by convention all my walks start at a special all my closed walks basically start at a special vertex or something like that. So whenever you are um, you could even artificially add a vertex if you do your graph, if you want to be kind of really picky about that. But even otherwise, I think I mean, hopefully the fact that the same walk can have, like, you can start anywhere is not terribly confusing. I don't remember exactly how it's done, what the convention is in the book, so I'll go back and sort of double check it. But some people actually prefer to fix a special vertex so that all your walks are kind of anchored at a particular starting point. But then you have to worry about, like, if your subset does not have that special vertex, then do you have to you can follow a convention where you say that you always start your walks at the lowest indexed vertex or something like that. So I'll do a quick double check of what is the convention that's followed in the book. But basically the idea is uh, modulo the question of the starting point, ending point. Hopefully the big idea is clear. The big idea is that you are expressing the thing that you want to get to in terms of an intersection of things that are easier to work with, but it's a bigger set of things. So when you're looking at closed walks, you get all these garbage walks which are not paths and you're not interested in those, or which are not cycles and you're not interested in those. And then the inclusion exclusion formula is basically, you can think of it as a weeding out process. You do this plus minus dance to basically systematically get rid of all the things that you're not interested in, because essentially what you want here, so I think I've not written this quite correctly. So what we want here is the intersection of all the AVs over all the vertices, and that gives you precisely what you're looking for. Okay, so are there any questions about this, like the overall approach?
No, as a question, because I lost somewhere, and probably I need to revisit it to absorb the things and to
Okay,
be
all right, no worries.
to make it my own because I
Yeah,
can
yeah.
understand that yes, things are going on fine.
Right. Okay, sure. Maybe when you have a chance, take a look at the recording, or maybe it may be faster for you to just look at the description in the book. So what I'll do is I'll post a link to the book in the forum. I mean, a pointer to the specific subsection where this is
Mhm.
described. So you can either read through that or skim through the video, whatever is convenient. But yeah, I mean, there are two core ideas here to take away. One is the definition of the sets over which you want to take the intersection that
Mhm.
captures the quantity that you're interested in. So, in my opinion, this was the first thing about this algorithm that was really clever, to identify that we want to work with the AVs, their intersection produces the number of Hamiltonian cycles. I think that was really interesting. And then the point is that, okay, you can write down this intersection, say this is what you want, and you can mechanically write down the inclusion exclusion formula. There's really nothing special about just plugging in the formula. But then if you want to turn this into an algorithm, then what is the algorithm? The summation is a for loop. It's going over all subsets. And inside the for loop, what do we have to do? We have to compute whatever is sitting inside the summation. And then depending on whether the subset was even sized or odd sized, we have to add that quantity to a cumulative sum that we are maintaining. So the point is that this algorithm is only complete when we have a description of how we can compute this quantity. So all that preamble we did with matrix exponentiation was to say that, well, this quantity here, if you look at the semantics of it, really corresponds to counting closed walks of length n in a certain subgraph of your graph. So what you're going to do is you're going to delete all the columns indexed by x in your adjacency matrix, and in the remaining matrix you raise it to the nth power. You take the diagonal entries, those give you closed walks. You can add them up to get this quantity here. That is kind of the idea. um, so yeah, basically the question is, can you come up with the right notion of the AVs, and can you come up with an algorithm that computes whatever it is that is sitting inside this sum? So normally you will basically, the design of the AVs has to satisfy two things. First of all, their intersection should count the thing that you're interested in counting. But when you take these intersections of the complements over the subsets, that should be something that is easy to compute. Because if we don't know how to compute that, then this whole method is going to basically go bust. We will not be able to use it. So those are the two things that your AVs should satisfy. And this is one example where this actually happens, right? The intersection of the AVs captures exactly what you're looking for, and the intersection of AV complements is simply some matrix multiplication operation. Once you convince yourself of the correctness of that, you have the whole algorithm. And the main advantage over DP is the fact that you save space. You don't need to keep track of a big DP table. Other than that, I think it's just a really cool algorithm, a very neat idea. The fact that you can use inclusion exclusion in this way. So in the lecture videos, we do the same method for chromatic number. So hopefully, if you haven't seen that yet, if you see it now, it should make a little more sense with this backdrop. Um, the assignment problem basically does something a little more general than Hamiltonian paths, something called Steiner trees, which is a generalization also of spanning trees. I would say try to, um, give it a shot. I think we are almost at the 1.5 hour mark now, so I don't want to belabor you further in this session. But if you want a bit of a spoiler, basically the next section in the book after the Hamiltonian path, it talks about Steiner trees, and that's what the assignment problem is really based on. So the assignment problem is really designed to encourage a little bit of additional reading and thinking. So take a look. But in case something is not clear, and I realize that we are running a bit tight on deadlines, so if you just tag me in the forum and let me know if you think an additional discussion will be helpful, I'm happy to hop on an informal call or a recorded session anytime between now and the deadline. So just let me know. And in the meantime, I hope that this introduction to the method was useful. If any aspect of this is still confusing, again, just post your question and tag me in the forum, and I will follow up. I'm now logging in more regularly. I don't know, somehow my email notifications were broken before. I wasn't getting them, so I didn't realize that there was all this activity, but I'll try to be more regular going forward. So yeah, so thanks very much for joining me in today's live session. I think we can close off the streaming here. I'm happy to stay back if you have anything more that you want to chat about.